There is a cruel truth buried in the structure of the universe. The stars are not separated by distance alone, they're separated by law. No matter how powerful our engines become, no matter how advanced our civilizations grow, the universe has imposed a speed limit, a hard boundary, a cosmic rule written into the fabric of reality itself. Nothing with mass can travel faster than light. And when you begin to run the numbers, the implications are staggering. The nearest star is over 4 years away at light speed. The nearest galaxy? 2.5 million years. Even if humanity mastered fusion drives, antimatter propulsion or nuclear pulse engines, even if we could accelerate a ship to a meaningful fraction of the speed of light, interstellar civilization would still be painfully slow, fragile and isolated. The universe is vast in a way our intuition is not built to comprehend, so if expansion is possible at all, it requires cheating. Not by going faster, but by changing the rules of distance itself. And this is where science fiction steps in, not to abandon physics, but to push it to breaking point. And Halo's answer to this problem is Slipspace, and surprisingly, it's one of the most disciplined attempts in fiction to make faster than light travel feel like a physics problem and not a magic trick. Hey everyone, welcome back to The Lounge, a space for curiosity, clarity and quiet thought. Throughout the ages, humans have looked up to the night sky with longing and wonder. We've gazed into the eternal cosmos and desired deeply to discover its secrets and mysteries. With the gradual progress of technology and a great deal of human ingenuity, we have finally reached an age where there is a constant human presence in space. But we're not sailing between stars and colonising worlds aplenty. We've not really even left our own planet's vicinity with manned missions, and in truth, have regressed quite tremendously. However, this is seemingly on the cusp of change once again. Recent developments in space has seen numerous private enterprises developing innovations that are paving the way for human expansion, but in a more conservative effort than originally expected. Plans for Mars colonisation have repeatedly shifted as the reality of interplanetary colonisation proves far more complex than early optimism suggested. This is a very sound change in plans. The target of landing and colonising Mars by 2030, a mere 4 years away at this point, still presents a great many obstacles that we've yet to demonstrate the capacity to address. It is a much more sound idea to shift focus to the moon, fully develop the technical capabilities, the logistics, the early habitats, way stations, and other innovations which will unlock interplanetary space to humanity. I'd always said, even so far back as being a teenager, that within my lifetime I would look up to the moon and see lights upon its surface. That is seemingly more achievable now than it has at any other time in human history, and that's mainly possible by the efforts of only a few private enterprises. With numerous extremely well-funded private companies all now focused on commercializing space, the future of human endeavour in the inky black cosmos high above seems to be growing closer by the day. But to stretch the forecast out far into the future, attaining interplanetary human civilization will only satiate human pioneering spirit and natural proclivity to discovery for so long. At some point, inevitably, someone will look beyond our solar system and begin devising a way to go there. And in truth, they already have. But the universe imposes some barriers to that particular endeavour that are more insurmountable than maintaining a survivable, breathable atmosphere or establishing a prefabricated colony on a nearby terrestrial body. The universe poses two distinct problems that we currently have no solutions for: distance and time, or rather speed. And that's where our conversation turns from conventional to relativistic, and Halo's method may unironically hold one of the most logical, if hypothetical, solutions to this most enduring of problems. Relativity doesn't just say light is fast, it says that light is special. The speed of light isn't merely a speed limit, it's a structural feature of space-time itself, baked into the geometry of reality. Every observer, no matter how fast they're moving, will measure the same value, roughly 300 million meters per second. And Einstein captured the consequence of that in perhaps the most famous equation ever written: E equals mc squared. Energy equals mass times the speed of light squared. At first glance it looks simple, elegant even, almost harmless, but hidden inside that equation is a terrifying implication. Mass and energy are interchangeable, and the speed of light is the conversion factor squared. That number is enormous. It means that as an object accelerates towards light speed, the energy required doesn't increase linearly, it rises explosively. The closer you get, the more universe resists you. The energy required to accelerate you grows without bound. Accelerating a 1,000-ton spacecraft to 10% the speed of light would require energy comparable to the total output of humanity over 1.5 years. Time dilates, length contracts. From the outside, your clock's slow. From your perspective, the universe compresses. To actually cross the light barrier would require infinite energy, and physics is deeply allergic to infinites. They are nature's way of saying, you hit a boundary. This means interstellar travel isn't just hard, it's forbidden under classical motion in survivable timeframes. Even reaching a significant fraction of light speed would push us to the edge of survivability. At 10% of light speed, a tiny grain of dust carries the same kinetic energy as an explosive. At higher fractions, a collision with a pebble is equivalent to a nuclear detonation. Space is not empty, it's a shooting gallery of micrometeoroids, ice crystals and atomic debris. At relativistic velocities, the universe becomes a sandblaster made of bullets. And then there's the energy bill. To accelerate a modest spacecraft to relativistic speeds would require energy on the scale of nations. Chemical rockets are hopelessly inefficient. Even nuclear fission barely scratches the problem. You start needing propulsion concepts that border on science fiction themselves. Fusion drives, antimatter annihilation, beam-powered sails, exotic thrust systems we have not yet learned to build. We are not just fighting distance. We are fighting the architecture of reality. So, physicists have spent decades asking a loophole question. What if the ship never moves faster than light, but space-time does? This is the philosophical seed behind every serious faster-than-light concept. Warp the road, don't speed the car. Science fiction has wrestled with this wall for generations. Halo's answer is Slipspace. In Halo, humanity solves this with the Shor-Fujikawa Translight engine, not by brute force acceleration, but by engineering space-time itself. The drive uses an absurdly advanced particle accelerator to generate microscopic black holes. Under normal conditions, such a black hole would evaporate almost instantly via Hawking radiation, a quantum process where black holes bleed energy and disappear. But the engine captures it, feeds it energy, stabilizes it and forces it to open into a traversable throat, a wormhole, not just across space but into a higher dimensional structure called slipstream space. Slipspace is not another universe, it's a deeper layer of the same one, a folded geometry where distances collapse. Travelling through it is like stepping off a flat map and walking through the third dimension to reach a distant point instantly. But Slipspace is hostile. It does not obey classical physics. Causality becomes unstable, distances behave strangely. Without protection, normal matter would not survive transit. So, the engine generates a quantum-stabilized bubble, a shell of ordinary spacetime wrapped around the ship, and inside the bubble, physics behaves normally, while outside of it, reality is negotiable. The ship is not flying through slipspace, it is carrying its own local universe with it. And that idea, as bizarre as it sounds, has echoes in real theoretical physics. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's equations that sounded like science fiction, even to physicists. Today, it's known as the Alcubierre drive, and its central idea is deceptively simple. It doesn't move a ship, it moves space-time. Instead of pushing a vessel through space, the drive reshapes the geometry around it. Space contracts in front of the craft and expands behind it, creating a wave, a bubble, that carries the ship forward. Inside that bubble, the vessel is technically at rest. It never locally exceeds the speed of light. To the crew, gravity behaves normally, clocks tick normally. From their perspective, they're not breaking the universe's rules. They're riding a loophole in its geometry. And that distinction matters, because Einstein's relativity doesn't forbid space itself from moving faster than light. In fact, the expansion of the universe already does exactly that. Distant galaxies are receding from us faster than light, not because they're outrunning photons, but because space itself between us is stretching. The Alcubierre model asks, what if we could engineer that stretching on demand? Not outrun light, but rearrange distance. Now add a second idea layered on top of that. Wormholes. A wormhole is not a tunnel dug through space, it's a shortcut through geometry. Imagine folding a sheet of paper so that two distant points touch. Punch a hole through the fold, and what was once a long journey across the page becomes a step across the seam. In relativity, wormholes emerge naturally as solutions to Einstein's field equations. They are mathematically legitimate structures, bridges connecting distant regions of spacetime. Some speculative models even propose the very fabric of spacetime itself is woven from quantum entangled particle pairs that wink in and out of existence, linked together across space by wormholes. The obstacle is stability. A wormhole throat wants to collapse instantly unless it's held open by exotic matter with negative energy density. We don't know how to manufacture such matter in useful quantities, but the equations themselves do not forbid it. They simply demand conditions we have not yet learned to create. Then there's the idea of higher dimensions. Modern theoretical physics, especially string theory and certain quantum gravity models, suggest that space-time may contain more dimensions than the 3 of space and 1 of time that we directly perceive. These extra dimensions may be compactified, curled up at scales too small to observe, or structured in ways that allow alternative geometric pathways through the universe. If distance behaves differently in higher dimensional topology, then what appears impossibly far in our familiar dimensions could, in principle at least, be much closer along a hidden geometric route. Slipspace takes all 3 of these speculative frameworks and stacks them. A warp bubble, inside a wormhole, threaded through higher dimensional geometry. It's not realistic in an engineering sense, at least not with modern or even near future engineering, but then not many of these FTL concepts really are. But mathematically, it's shockingly coherent. Each layer is rooted in real theoretical work. Warp bubbles come from general relativity, wormholes come from the same equations, higher dimensions arise from serious attempts to unify gravity with quantum mechanics. None of these ideas are experimentally confirmed, but neither are they dismissed as nonsense. They live at the frontier where physics is still asking questions. And Halo doesn't ignore this frontier. It hand-waves the engineering a bit, but preserves the structure of the problem, and that's good science fiction. It doesn't break reality carelessly, it bends it along lines physicists already know exist. But faster-than-light travel carries a deeper threat than energy cost. It threatens time itself. According to relativity, if FTL travel exists, then in some reference frames, effects can precede causes. Messages could arrive before they're sent. Events could influence their own past. You don't just get fast travel, you get time travel. And time travel is where physics starts to look less like science and more like philosophy. Halo addresses this with something called particle reconciliation, a fictional mechanism where Slipspace enforces global consistency. Causality violations are healed, preventing paradoxes. While invented, the philosophy actually mirrors some real physics debates. Some theories argue the universe may enforce a form of chronology protection. Others propose a self-consistent timelines where paradoxes simply cannot form. Slipspace in this sense isn't ignoring causality, it's asserting that reality has built-in error correction. That's speculative, but it's intellectually honest speculation. But here's one of the smartest details. Slipspace isn't instantaneous. Journeys can take hours, days, even weeks. This preserves some narrative tension and physical plausibility. Traversing unstable topology would require constant recalculation. Tiny errors could mean catastrophic exit points. Longer distances would compound uncertainty. Think less teleportation, more navigating a storm in higher dimensional space. Better engines don't just go faster, they calculate safer paths. But could anything like Slipspace ever exist? Not as described, no. We are nowhere near the energy scales required to engineer spacetime. We don't know how to create stable negative energy in useful amounts. We don't know if higher dimensional shortcuts are physically real. But we also don't know whether or not they're impossible. Every serious FTL concept, warp drives, wormholes, quantum tunneling spacetime, emerges from real equations. They're not forbidden by logic, they're forbidden by our current capabilities. But human history is a story of capabilities changing. Flight was impossible until it wasn't. Nuclear energy was a fantasy until it wasn't. Space travel was a myth until it wasn't. The universe is not obligated to be easy, but it's also not obligated to remain closed forever. Whether humanity reaches the stars through warp bubbles, engineered wormholes, cryogenic arc ships, or technologies we haven't yet imagined, the desire to cross that distance is already written into us. Slipspace is not a prediction, it's a thought experiment, a reminder that physics is not a prison, it's a puzzle. And every generation pushes a little further into the unknown, discovering that reality is stranger, deeper, and more flexible than we once believed. The stars may be separated by law, but laws are meant to be understood, and understanding is the first step towards transcendence. The question is not whether the universe allows us to travel between the stars. The question is whether we will become the kind of civilization capable of asking the right questions long enough to find out. And until next time.